Hi, my name is James Keller. I am an undergraduate researcher working for Dr. Jeremy Levy at the University of Pittsburgh. Today, I'll be talking about lithium aluminate strontium titanate nanostructures being investigated using cryogenic piezo response force microscopy. Our group is interested in an emerging field of research called correlated nanoelectronics, where we take some of these intrinsic properties to bulk complex oxides, such as superconductivity, and add them to the paradigm of semiconductor electronics, as seen here with a gallium arsenide interferometer. So by combining these two things, we create added richness to these mesoscopic devices, adding more degrees of freedom to them. And in return, these novel devices allow us to reveal properties of these oxides, such as some of the mechanisms behind superconductivity. Together, we can create novel quantum phases and devices with this material. A complex oxide we're interested in is lithium aluminate strontium titanate. Specifically, we are interested in LAO. So when LAO is deposited, pulse laser deposited onto bulk strontium titanate, it forms a highly mobile two-dimensional electron gas. At the interface of LAO-STO, there exist many remarkable properties such as superconductivity and spin orbit coupling. However, when LAO is grown at a certain number of unit cells, it can show in a conducting or insulating state. However, when we grow LAO at 3 unit cells, we can use a property called the metal insulator transition to create nanoelectronics on demand. And we can do this because LAO is typically insulating at the thickness of 3 unit cells. However, by essentially creating a top gate on the LAO surface by essentially dragging AFM tip with the positive voltage on the surface, we can create essentially a top gate on the LAO which tunes the LAO-STO interface. And for these, this technique is highly precise, allowing us to create nanowires up to 2 nanometers thick, and we can end up creating nano devices by erasing certain points in these nanowires by applying a negative current. This allows us to create novel nanoelectronics, not unlike you would by using an Etch-a-Sketch. And so using this technique, this allows us to create some novel nanoelectronics devices, which allows us to learn more about the nature of this material. Specifically, we have created single electron transistors, ballistic electron waveguides, and intercrosses, which are essentially 4-terminal ballistic electron waveguides. And so using some of these devices, such as ballistic electron waveguides, we have found more novel effects in the LAO-STO system. Specifically, we have shown that there's a quantized conductance scaling at intra-values of E squared over Planck bar, indicating that there is a scattering length. Specifically, we see about 20 micron meters, which is much greater than our channel length, indicating electron transport. Moreover, as seen in this graph here, that due to the energy band gaps, we can also see evidence of electron pairing. And so this naturally arises the question, why is this occurring? And how does it occur? And so we believe that these effects are structural in nature. We believe that some of these effects are related to the ferroelectric domains within LAO-STO nanostructures. So this is because at the critical temperature of 105 Kelvin, the ferroelectric domain is strontium titanate strain. This is due to a cubic 2 tetrahedral structural phase transition in the STO lattice. These resulting new domains have interesting properties at their domain walls. Specifically, we have seen evidence of superconductivity, electron pairing, and the ability to locally tune STO at these domain walls. Specifically, for our purposes, since since we have shown that the Z-oriented region is conducting and elongated, that these parallax domains should be preserved to cryogenic temperatures and should correspond to our nanodevices. And so that we have some questions about these parallax domains. Specifically, we want to know, can we experimentally verify and visualize these parallax domains? Specifically, using nanodevices, which we only have hypothesized parallax domains for, such as with a nanocross, can we map that specifically? And moreover, we want to understand how does gate voltage affect these ferroelastic domain structures? How does gate voltage affect our 1 to 2D nanostructures also? And we believe that we can do this using a technique called piezo responsive force microscopy. Specifically, we believe that we can map these ferroelastic domains using PFM. And so this is because we believe this is because of the piezoelectric effect in LAO STO. Specifically, LAO STO is piezoelectric material, meaning that a change in carrier density causes a surface deformation with the inverse holding true. And so from this, we have shown several interesting properties concerning that. Specifically, we have shown that the piezoelectric strain tensor can be directly correlated to the local carrier density under certain regimes. Moreover, we have shown that this effect is non-destructive, and I'll get into that later, why we care about that so much, by taking essentially IV curves from before and after running PFM and seeing that they're the same, indicating that the structure is essentially unchanged from this technique. And so piezo response force microscopy is a technique, an SPM technique, which utilizes the piezoelectric effect to measure AFM tip deflections. Specifically, what we do is apply an AC current to the nanowire, and regions with higher with higher conductance will respond with a higher piezo response. And so we want to do this because this is a non-destructive and atomically precise technique, because typical AFM measurements actually erase the wire as they're being taken. So if we have a device that's working, we want to keep it working and not have it erased. So what we would like to do is actually extend this measurement to cryogenic temperatures where we see these interesting quantum properties. And so we want to actually do the opposite of what I talked about in the previous slide, and utilize inverse piezo response force microscopy, where we invoke the piezoelectric effect by force probing the LAO surface. And specifically, what we want to do is observe changes in carrier density through changes in transport measurement. We believe that by doing this, we can actually take images of these ferroelastic domain structures, as seen in the picture below. And what we want to do is show that some of these transport measurements come from the ferroelastic domain, specifically as shown in the group above, that as indicated here, that these by essentially these white strips being ferroelastic domain boundaries, that the graded changes in voltage occur within these regions, in these regions, sort of indicating that, as what we believe, that these domain boundaries are related to some of the intrinsic properties of LAO STO. And so the question then becomes, can we do these experiments? Specifically, how can we create a system which can house these experiments? And so what we wanted to do is so what I was doing was taking a homemade, a normal high vacuum AFM, the Joule AFM, and turn that into a cryogenic AFM. Specifically, us as a group, we added a liquid flow helium cryostat to the AFM so that we could get low enough temperatures to run these experiments and the necessary electronics. This The device was actually running along pretty smoothly until we had encountered issues with pulling a vacuum. And so due to executive decision and the arrival of a new instrument, we decided to switch to this instrument, the Omicron Variable Temperature AFM. One, because it offers some better capabilities such as ultra high vacuum and the ability to pattern our nano devices using a newfound technique that of ours called ultra low voltage e-beam lithography, which allows us to write our devices up to 10,000 times faster, which is much. And so in all, this device shows much more promising to running our experiment than the old one did. So in all, what we would like to do is use cryogenic PFM to investigate LAO STO nanostructures and using some of these inherent electromechanical properties of LAO STO. Specifically, what we want to do is image these ferroelectric domain structures and understand how those domain structures relate to some of this nanostructures properties and so that we can understand more about the nature of some of these fundamental properties of LAO STO. Questions? That's it. Thank you.